In the last class, we have studied the architecture of PIC processor. Today, we shall look at the instruction set of the PIC family of processors. PIC has got very simple instruction set. Typically, it has about 35 instructions. These instructions can be grouped into three categories: byte-oriented operations, bit-oriented operations, literal and control operations. For mid-range PIC processors, instructions are of typically 14-bit long. All instructions execute in one cycle unless some conditional test is true and the next instruction has to be skipped, or the content of PC is explicitly changed because of the instruction. In those cases, execution of each instruction takes about 2 cycles. The instruction format is different for different kind of operations. We have already seen that we have got byte-oriented instructions, bit-oriented instructions. And for these instructions, the structure looks something like this. In a byte-oriented operation, you specify a 7-bit file register address, which is typically the memory location. The 7th bit is a destination bit, which is 0 when we are using the working register W as a destination. Otherwise, it is set to 1 when the register that you have specified in 0 to 6th bit is the destination itself. 8 to 13 bits are storing the opcode, that is the binary code for specific operation. For the bit-oriented operation, the interesting feature is using 3 bits, you can actually specify exactly the bit number which is to be checked or modified in the file that you have specified in the address. Here also 10 to 13 bits are used for the opcode. In a literal and control operations, the structure is slightly different. In this case, we use immediate value. For a general instruction, the 8-bit literal or the immediate value forms part of the instruction. In case of call and go to instruction, you have got 11-bit literal value as part of the instruction. Now, these literal values provide for immediate mode addressing, and the data which is used in the literal value is part of your program memory itself. Interesting to note that your PC has got 13 bits and your call and go to instructions have provision for specifying 11-bit target address value. So, the upper 2 bits come from PC latch high register, that bit number 3 and 4 is loaded for upper 2 bits. So, therefore, when you are making a call or go to, the most significant 2 bits are always specified through PC latch register. This is a very interesting feature of PIC instruction set, particularly the instructions which control program flow. Now, let us look at addressing mode. What is addressing mode? Use addressing mode for specifying operands in an instruction. PIC supports direct addressing, indirect addressing, as well as immediate mode addressing. We have already seen the structure of instructions which support immediate mode addressing. Now, let us see how direct addressing is supported in PIC. In the PIC, these 2 bits RP1 and RP0, which are part of status register, they are used for selecting what is called bank. And in the bank, the address is specified by these 8 bits, which is part of the instructions. These bits which we have from the instructions actually makes the choice of the location in a typical bank. So these 2 bits are used for selecting the bank, and the offset in the bank is specified by these bits which are part of the instructions. So therefore, in each of these banks I can select a location by specifying this 7-bit address in the instruction itself. In indirect addressing, PIC uses a slightly more complex structure. The full 8-bit register address is first written into FSR, which is a special purpose register. And FSR serves as address pointer to any address throughout the entire register file. And the subsequent direct access of another special function register, INDF, will actually access the register file using the content of FSR as a pointer to the location of the operand. So in this case, what it implies is that you first load the FSR register with the value. Now these value you need to load in the FSR register through a instruction. The bank select is via IRP bit, which is part of the status register and the 7th bit in the FSR register. The remaining 7 bits, the 7 bits is used for selecting the offset in the bank. Now once you have loaded FSR register with this value, what you need to do is you need to access INDF register. Once you access INDF register, PIC actually uses the address in the FSR register to access operand in the memory. So actually you can see that in indirect addressing in the PIC actually requires use of not only one instruction but 2 instructions for specifying the address. There are a variety of instructions in PIC. Although I have already told you this number of instructions is much smaller compared to that of a typical CISC processor. If you are familiar with 8086 or 8085, you will find that compared to 8086, the number of instructions here is much less. And what is more interesting to note is the addressing modes. The number of addressing modes that are supported is also much less compared to any CISC processor. Let's first look at byte-oriented operations. These byte-oriented operations are primarily targeted for arithmetic and logical operations as well as for data movement. We have shown some examples here. These instructions add WFFT is an instruction for addition. When it executes, what happens? The contents of register W, okay, is added with register F, and if D equal to 0, the result is stored in W, else the result is stored in the register F. In fact, D is indicating your destination bit, which we had discussed in the instruction format. So actually when you will be using this, you will be writing it in this form. So this actually represents a memory location in the bank, and this memory is part of the PIC chip itself. It's in the register bank. That location you are specifying, and then you are telling this is 0. That means the result will be stored in W itself. So you add the content of this location with the content of the working register W and store the result back in W. This is an instructions for clearing the content. So contents of register F are cleared, and Z bit is also part of the status register is set. And here also you will be specifying exactly a location. Similarly, this is an example of a data move instruction. Here you are moving data from W register to register F. Now interestingly, when you have to select the bank, that bank select operations you have to do prior to execution of this instruction. That means you first select the bank, and once you select the bank, then only you execute these instructions so that the correct location is accessed. Let's look at some more byte oriented operations. Now this is a pretty interesting instruction. This is an example of a conditional branching instruction. In the PIC, we have got go to instruction, which is a unconditional branch. We also have got conditional branch. This is an example of that kind of an instructions. But in case of conditional branch, you skip only next instructions. So it's not that you can make a conditional jump to any arbitrary location in memory. This is a very distinctive feature of PIC, and you should make note of it. Now this instruction that we are looking at here is interesting in various ways, because this indicates an operation as well as branching. It is not just a simple branching instruction. In this case, you decrement the register F, you place the result in F or W depending on the value of your destination bit D, and then you may skip the next instruction if the result is 0. Which result? After decrement, the result that you are getting, if that result is 0, then you skip the next instruction. So this is just not conditional branching, this is doing an arithmetic operation combined with conditional branching. This is a very interesting feature. Another interesting thing what happens is that when this result is 0, the PIC has to skip the next instruction. And if you remember the way the PIC instructions are executed, I told you in the last class that while an instruction is being executed, the next instruction is fetched. Now in this case what happens? The next instruction which has been fetched cannot be executed. So that instruction has to be replaced by nope or no operation. So effectively this instruction would require now 2 cycles for execution. That is, when the result is 0, this instruction will actually require 2 cycles for execution and not just 1 cycle for execution. Along with it, I am showing another example, which is simple decrement. So in this case, you simply decrement the register and place the result depending on the value of D either in W or F, and this would also affect the 0 flag of the status register. Now one interesting thing you should note with respect to this previous instruction, that is a combination of an arithmetic operation and conditional branching into one instruction. What is the motivation for designing such instructions? Because similar instructions you will find in other microcontrollers and processors targeted for embedded systems. This increases what we call code density. That is, instead of using 2 instructions, that is one instruction to decrement and then jump, you are using a single instruction. So the number of memory locations that your code would occupy can decrease. If it decreases, what does that mean? You require less memory, and obviously when you are working in an embedded system, you try to work with less memory, and less memory would also imply less power consumption. Let's look at now literal operations. Now in the literal operations, we actually use immediate mode addressing. In this case, these are all direct operations, that is where your data is part of the instruction itself. So, this literal k, which is part of your instruction, you are adding to the content of register W. So, if you look at this example, in this example, this 5 is actually added with the content of W, and the result would be stored in W itself. In this case, you are moving a particular value into the W register. So, now if we can summarize what we have seen in particular for byte oriented data transfer operations, then we have provision for writing onto the W register through immediate mode. That is, the literals can be copied to the W register. In fact, we can also have arithmetic operations done with the immediate operands involving W register. Also, we can do data movements, in the sense that data can be copied from W register onto RAM locations as well as vice versa. So, these are the basic data transfer operations that are supported in the PIC instruction set. We have also seen that there are instructions by which we can clear the content of the registers, that is, we can make them all 0. And this is interesting because at times you require the register contents to be cleared for various kinds of initialization tasks. Initialization not only for arithmetic operations, for also doing hardware interfacing operations. The last instruction that we are referring to here is swap instruction. Now, swap instruction, what does it do? It swaps the nibbles of a register. That means it exchanges, and this exchange takes place in a single instruction. Typically, when we try to exchange value of 2 memory locations, we require a third, a temporary location. And this kind of exchange operations involving more than one instruction can also lead to various kinds of problems if there is an interrupt occurring in between. Then the swap may not take place correctly. So, if swap can be provided as an atomic instruction, then we can guarantee that swap operation is taking place without any disturbance, and the swap is correctly swapping the data values. In case of PIC, we have got swap operation for nibbles, and it can be operated in various interesting ways. We can swap the 4 bits, okay, lower 4 bits with higher 4 bits in the W register, and we can also store that content into another register as well. Now, obviously, why is PIC supporting swap instruction? Swap instruction is required for what we call various kinds of synchronizing construct implementations when we have concurrent processing supported in an embedded system. These concurrent threads are what? If from the external world I need to support multiple operations, take for example, when we had discussed in the introductory course also, I have got a temperature controller which is sensing the temperature. This temperature controller can also be modified by the user to set a value, and it also is recording the real-time clock. Now, it is doing therefore what? 3 tasks. These are 3 concurrent tasks which are to be supported on the embedded system. And if these 3 tasks are accessing a common memory location or executing a common code, we have to make sure that only one of the tasks is accessing that common memory location or executing that common code. In order to ensure exclusive access, we need to implement various kinds of lock variables. In fact, the swap instruction supports or facilitates implementations of these kind of locking schemes. what we call formally as synchronizing primitives. Now let's look at more information. Let's look at and understand more information about arithmetic and logical instructions. PIC doesn't support complex arithmetic operations. It supports simple addition and subtraction. Because PIC in its basic form is not really targeted for, say, signal processing applications or number crunching applications. It is typically targeted for simple control or instrumentation applications. In that case, addition and subtraction operations actually can meet majority of requirements. But I am not telling that multiplication is not required. Multiplication and division is also required, but then that has to be implemented with the help of these addition and subtraction instructions. And these flags C, DC and Z are affected by these arithmetic instructions. Since subtraction is performed like addition of a negative value, that the C flag behaves like a borrow flag when actually subtraction operation is executed. The logic unit of PIC has the capability of performing operations like AND or XOR, complementing, as well as that of rotation, just like any other standard microprocessor or microcontroller. We shall look at rotation instructions. Now typically rotation instruction rotates a register content through the flag C. So carry flag is involved when we are doing the rotations. So bits move by one bit to the left or to the right, depending on whether you are doing a rotation left or rotation right instruction. The bit which comes out of a register is written into flag C, and the value of C flag is written in a bit on the opposite side of the register, of the target register. That means that original content of C now becomes what? The least significant bit, if you are looking at that way, either least significant bit or the most significant bit of the target register. So this is an example of a rotation instruction that we have shown here. So copy, in this case, you are copying F into F or W and rotate F or W right through the carry bit. Now F or W is, F is a register file itself, or W is the working register. So this is how we implement the rotation instructions. Now let us look at bit oriented operations. Now byte oriented operations obviously is targeted for primarily data movement as well as arithmetic operations. But when we look at bit oriented operations, you should understand that why at all these bit oriented operations are being implemented, because you can say that fine, if I can do, if I can select a correct combination, okay, of logical operations, I can access and modify the bits. But that becomes again what? A combination of multiple instructions. Now if I need to do lots of bit manipulations, and these bit manipulations are essential when we have hardware flags or hardware interfaces to be manipulated and controlled. As a microcontroller targeted for embedded applications, it has got number of peripherals on chip. Various control bits of these peripherals have to be manipulated through softwares. I/O operations are needed to be controlled through softwares. These operations in most of the cases are bit oriented operations, and that is why you will find a pretty powerful set of bit oriented instructions supported in PIC microprocessor, PIC processor. So let us take some examples. This example is a very simple case where you are setting a particular bit in a register F. So here if you take explicit example, this is the register that we are referring to, and we are referring to which bit? We are referring to 5th bit. And what we are doing? we are explicitly setting the corresponding bit. Okay. Similarly, we can do this. This is a kind of, again, an example of a branching instruction. Okay. And this branching instruction is on the basis of testing a particular bit of a register F. So, what we say that we skip the next instruction if the bit B is 0 in the target register. So, this is the target register and we are actually checking for the bit 2. This is again a conditional branch instruction. So, conditional branch instruction means you will be skipping the next instruction only. So, instructions we have seen, therefore, the BCF and BSF perform set or clear one bit anywhere in memory. And bit operations consist of following micro operations. CPU reads the complete byte, CPU changes one bit in it and then writes the entire byte back. So, it is, just try to look at this, because this has got a various interesting significance attached to it. This is read, modify, write, and this read, modify, write is taking place in an atomic fashion. This read, modify, write is taking place again in an atomic fashion. Obviously, the issue that comes up is that when you are reading a data from an external port, you are reading a data and you are modifying it, and this modification requires definitely a finite time period, and during that period if there is a change in the input, because you are reading the data from the port input pin from the external source, what happens? So, we shall discuss this problem when we actually discuss the peripherals, that is digital I/O ports which are supported on PIC. But this read, modify, write is again an atomic operation. The advantage of the atomic operation is this cannot be interrupted by an external interrupt. The control instructions are primarily program and processor control. In this case, go to is effectively unconditional branch. You can jump from any location to any other location. And in this case, we have got an 11 bit and the remaining 2 bits is coming from the PC latch high. And same thing is true for subroutine. The upper 2 bits of PC is loaded from PC latch, and these are the bits corresponding to the PC latch high register. There are some more interesting instructions, control instructions in PIC. This is an instruction ret fee or return from interrupt with interrupt enable. This happens when this is typically executed when you return from an interrupt service routine. Now, what is the difference between returning from an interrupt service routine and returning from subroutine? Effectively nothing, because in both the cases you need to get the return address from the stack. In case of PIC, you have got hardware stack. So, the return address will be stored in the hardware stack and you have to get the return address from that hardware stack. But in this case, this instruction typically re-enables the interrupts. What does that mean? It means that when an interrupt occurs and you are servicing the interrupt can be disabled so that the current interrupt service routine is not further interrupted. Now, this is also important for PIC. Why? How this interrupt, that is your coupling of the interrupt service routines to be managed. Why this is important for PIC? Because PIC can support only 8, that is on the mid-range processors, we have got the stack of fixed size, hardware stack of fixed size. So I cannot permit any arbitrary nesting of interrupts and subroutine call. Okay. So I need to enable or disable interrupts whenever I am servicing the interrupts. And when we return from an interrupt, we should enable the interrupts. So these RET5 instructions typically enable interrupts. Then there is a sleep mode of PIC, and this is a power saving mode. That means when no useful operation is being done, the PIC processor should be put to sleep. So there is a specific instruction by which the PIC processor can be put to standby mode. The other instruction is with relation to watchdog timer. You can clear the watchdog timer because I have told you that if watchdog timer finishes its counting, okay, or at after a particular time period, and watchdog timer is supposed to interrupt the system, it may reset the system. Ideally, it should reset the system, and I have already discussed why watchdog timer is required. So if you do not want the watchdog timer to really reset the system, you would like it to be cleared periodically or reprogrammed periodically. So this clear watchdog timer is an instruction for clearing the content of the watchdog timer. And if you see how these program flow control instructions, so go to, call and return. See, call and return instructions obviously using hardware stack, and which is independent of the internal RAM, and it is limited to 8 levels. So even if you are considering a scenario, an ID and a kind of a hypothetical scenario where you assume there are no external interrupts, then also you cannot have arbitrary nesting of subroutine calls because your maximum depth is fixed. There is also a very interesting instruction. Another interesting instruction. This instruction is again a return instruction, except that before coming back from a subprogram, a constant defined by instruction operand k is written in the W register. This is again what? This is an interesting form because this is a particular value which is written onto the W register when you are returning from a subroutine call. So this is, you are returning a particular value in the subroutine call and using a single instruction. Again, you will find that this instruction enables you returning a value in W register, and this would lead to very interesting tricks that you can play with your code, and we shall see such examples now. Let us start looking at some of these example codes. Because what you have learned so far, you have learned instructions. Now using these instructions, you have to write small codes so that the processor can do useful operations. This is a very simple example, that of a 16-bit counter. So obviously if I have to implement a 16-bit counter, what I need to do? I need to use 2 memory locations and not 1, because effectively each memory location is of length 8 bits. Okay? And in this case what I am doing? I am using 2 locations, one I am calling count H and another I am calling count L. And I am decrementing, and I am decrementing count H, count L, and here I am checking that if count L is 0, okay, and what we are checking for? This we are checking that depending on the condition, we shall be whether decrement count L or we shall be decrementing count H. Fine. Now the interesting feature is, if an interrupt occurs, try to understand this, if an interrupt occurs while this code is in execution, what can happen? Your decrement may not take place correctly, because your counter is not getting decremented by an atomic operation. Is this clear? Because there are 2 bytes and they have to be decremented. So what you need to do is that for the purpose of atomic, if you want to ensure atomic decrement operation on this counter, you need to protect this code. That means you need to disable the interrupt from occurring. Let us look at another example. This example is for producing a square wave on one of these ports, because I told you that PIC microcontroller has got on-chip port. If you remember the architecture, we had shown ports, and we shall discuss how exactly these ports are to be used when we discuss these peripherals, but this is a small code example which actually interfaces with the port. Now, typically each port has got associated with a register, and you clear the content of the register, because if you want to write something onto the port, you would ideally like the content to be first cleared. The next thing is, these ports can be I/O ports. Okay, that means each pin can be configured as input pin or as output pin. Now, if you are doing that, then I need to pre-program that port and each pin of that port. So, in this case, we use a register called trace, and for each port, since we are talking about port A, we have got a trace A register, and we are clearing trace A register, making all pins of port A as output port. Now, you can see here again a usage of clear instruction for doing hardware programming. This is an example of usage of clear instruction for doing hardware programming. We are clearing off the trace A register to make each bit of port A as output port. Then next is very straightforward. We are just setting a particular pin 0, okay, and then what we are doing? We are going into NOP, a delay, then we are clearing that bit, and then we are going back and looping it in through an infinite loop. So, I should get a square wave, and depending on the delay, I have simply used NOP. I can add on NOP here as well, and depending on the delay, I can vary the period. I can also vary the duty ratio of this square wave. This is an example of branching, and obviously you know that when we are using branching, the most interesting thing is that I shall be using typically this skip instruction. Okay. Now, in this case, we are declaring that a particular location, that is this equal flag, and this is what we are doing, a particular bit in that register, I am clearing that bit. Okay, so I am calling that bit as a, maybe that bit in that register as equal flag bit, and I am clearing that. Then I am moving these two, that is, we are moving the data content of the port A to W, content of port B is now subtracted from W, and the result is getting stored in W itself. And then I am doing a branch instruction, that is, this is basically checking the Z bit of the status, and depending on the Z bit of the status, we shall take an action. So, when we find that when we look at this, that is, Z bit is set, because when they will be clear, okay, that is, when both port A and port B content are equal, then 0 bit will be set. So, if the 0 bit is set, what we shall do? We shall now set the equal flag. If the 0 bit is clear, we shall skip this instruction. So, this is a simple case of a conditional code by which we can check whether the content of the two ports are same or not. In fact, any memory location for that matter can be checked in this fashion. This is another example, and this example uses actually indirect addressing. So, for most of the examples that we have seen there were using direct addressing. Now, in this case, I would like to clear the location from 20 to 7F in a particular bank. Okay. So, what we are doing? We are moving, this is a literal and immediate operand which we are moving into the W register. And then what we are doing? We are moving the content to FSR. Now, we are clearing this INDF. Okay. And then what we are doing? We are incrementing FSR. F actually means the result will be set back, and then we are going through this loop. Okay. Now, the interesting feature you should note here is these operation, how actually the clearing is taking place. We want to clear the locations from this to this. And how will this take place? It will take place because I am clearing INDF. INDF is a indirect addressing register. That means when I am trying to clear INDF, it essentially means that the register memory location or the register pointed to by FSR should get cleared. Is this clear? So, what we are doing? We are accessing this register INDF, and as we are accessing the register INDF, we are actually clearing the location pointed to by FSR. The initial location FSR was pointing to what? 20. Okay. So, that location will get cleared, and then what you are doing? You are incrementing FSR and you are going through that loop. Okay. As you are going through the loop, what we are checking here? This is actually this will do a skip when it is set. So, this loop will not be executed when you have reached 7F. If you are trying to increment beyond 7F, you will skip, otherwise you will be clearing the content from 20 to 7F location. This is an example of using indirect addressing. And in fact, what you have seen is, interestingly, an application where really indirect addressing is required, because here you are changing content of a memory location in a loop. So, you cannot really use the address directly as part of the instruction, because this address has to be constantly changed, that each step the address has to be incremented, and as we increment the address, we have to go back and clear the content. So, this is a simple usage of indirect addressing and how it is exactly used in PIC. Now, you have got the relative addressing and software relative addressing as well, because when you are actually doing any of these go to and call, what is the significance of the fact that the two addresses, that the most significant bit here is coming from PC latch high register? It means all your go to and call is in a sense PC relative, the relative to current PC value, because current PC value, the most significant bit is loaded onto PC latch high. So, whatever offset is coming, offset is a 11-bit offset which is part of the instruction. So, all your go to and call operations are PC relative. This is the key significance of the fact that the most significant bits are coming from PC latch high register. Let us look at this example, and this is a very interesting example because it illustrates various features which you can use in PIC. Now, here we are using a table lookup, and this code is primarily for that purpose. Initially, you are loading with the register W with 4, and then what we are doing? We are calling the subroutine table, and table actually would be referred to by the 11-bit offset. Okay. and then next instruction after call, what you are doing? You are moving the result, that is you are moving the result, this result will be result from the table, so you are moving into the result. Now, how you are getting that result? Just look at the subroutine table. Now, this table subroutine also uses a very interesting instruction. This instruction add WF is routine instruction in the sense that it can be used with any register, but here it is interesting because it is using PC, a program counter, okay. So, current PC low, a program counter, part of the program counter as operand. Now, this feature is not typically supported in many instruction set. That is, you really cannot use PC as an operand in an instruction, but PIC provides the support for this kind of an instruction. So, what it is doing now? If you see here, you will be loading that current content of W, okay, will be added to PCL, and you will be jumped to the current PCL plus W. So, the moment this offset is added, the current location is this PCL plus W, and this has been done through an arithmetic operation. We have not executed any branch instruction at all. This is very, very interesting. We have not executed any go to or conditional branch, we have just done an addition operation. And then what is happening? From here we are doing returning with a value loaded in W. And this is really the table lookup operation, because actually I am calling this subroutine, if you try to analyze it, I am calling this subroutine with an argument, okay. This argument is being specified here, okay. This argument is being used for indexing onto the table. How the indexing operation is taking place? By adding this value to the PCL. Once you add that value to the PCL, the next instruction which is to be executed will be at an appropriate offset. That means it is being indexed onto the table. What is the instruction from the table? The table is represented as a return LW instruction. So, what does that mean? In this case, you return by loading a particular value onto W. So, a complete table lookup operation has been implemented, and implemented pretty efficiently with pretty high code density. Because here what is happening is that I am adding this content of W to PCL to index onto the table, and which content I am looking onto is being specified by this argument. So, if I change this value, I shall return from the subroutine using executing some other return LW instruction. So, I shall return with a different value, and that is why this is implementing a table lookup operation. So, we have seen more or less variety of instructions, and we have also used some of these assembly directives. So, in an assembly language programming, you use not only the mnemonics, because our discussions have been so far in terms of the mnemonics for the instructions of PIC, and these mnemonics gets translated to its binary code by the assembler, but assembler also supports symbolic references to addresses and data, which facilitates your programming. But the assembler for PIC has to handle some other very interesting and important tasks, because PIC is not just a single processor, but a family of processors, and for that family there will be variations in number of configurational issues, variations in the stack size, variations in the instruction length, variations in the availability of different peripherals on chip. So, if you have to use an assembler for a family, then that assembler requires to be designed differently. So, in this case, you will find for a PIC family, while you are using your code for assembly, you also specify the specification of the target processor, and various informations are being provided to this MPSM assembler to what we call .inc file. In fact, if you are using an 8086 assembler or 8085 assembler, your processor configuration is pre-specified. It is part of the assembler itself. But here you are using assembler for a variety of processors. So you have to specify what is your target processor by selecting an appropriate .inc file. This is a very important exception here. Also, there is a device configuration register. The device configuration register programs your processor in variety of ways. And this configuration information is also to be provided. And in fact, these two features are nothing exceptional for PIC, because you will find when you are using these assemblers for a family of processors with various target applications, you need to provide information about the configuration of the processor and specification of the target processor for assembling or translation of this code. This is true even when we shall look at compilers. This assembler also supports what we call macro facility. Why? Because you have got 35 instructions which are very simple, and you might be using a combination of these instructions repeatedly in your code. So to facilitate programming, what you do, you define macro. So macro is what? Just a collection of assembly language instructions which can be called differently with a different name by appropriately defining it in your assembly language program. So this is an example where I have defined a macro, okay. So I am calling this macro bank1, and this bank1 macro, what is the function of this bank1 macro? It simply sets the appropriate bit in the status register so that you can select your bank1. So in your code, what you will be using? You will be simply using bank1. So bank1 would appear like a new instruction. The assembler would expand this instruction. That means this will be replaced by the actual instruction of the PIC. Obviously, when you use this macro, the length of the code increases, but what is the advantage? You are not using subroutines. So try to please be clear about the difference between subroutine and macro. The subroutine obviously implies an overhead. Why overhead? That is, when you are making a call, you are putting PC onto the hardware stack, and the next instruction that you have fetched, okay, is not what is going to be executed. Okay, so it will be executed depending on the literal value which is stored in the call. Okay, so the basic problem you should understand in this case is what? That the overhead which is involved because of this call instruction, which would now require effectively 2 cycles instead of 1 cycle. So all these overheads would be avoided if you use macro. So what we have done today, therefore, we have studied instruction set of PIC microcontrollers. We have looked at small code snippets, and we also know about MPSM and how it is different from assemblers of other processors. And you will use these instructions for developing different applications which we intend to do using PIC as a microcontroller. And we shall also see examples of these instructions, how they are used in conjunction with different on-chip peripherals that the PIC microcontroller offer. So if you have any questions, we can discuss them now. Yeah.
So if I add something to the program, PCL, and a carry is generated, is that forwarded to PC let H, so bit 0?
See, when we do an addition, see the question what you are telling, that if I add something to PC latch, what happens to the carry flag? Is that the question? When we add something to the PC low, the PC low, what happens to the overflow? Typically, when you use that, the target is that you should use it in such a way that it points to an appropriate location, because overflow is not really useful in any way. And this increment, I have shown you an example. This increment is to be used for specific purpose like table lookup.
In my table lookup example, By the time we execute the add WF instruction, we have already fetched an instruction from the memory. Right, so how do we actually go to the...
See, if you look into it, the question is when we are executing the add WF plus that is content of PCL being added with W, what happens to the next instruction? Obviously, the next instruction that you have fetched will not be executed. Just like any other branch instruction, I have to push in NOP, and this effective cycles required for execution of this instruction would be 2.
So is add WF do we push NOP after add WF each time, or only when?
See, let's try to. The question is whether we explicitly push NOP. The programmer does not explicitly push NOP in case of any of these branching instructions. What we are telling as NOP is automatically gets pushed in the pipeline, in the sense that the execution control logic is such that next instruction will not be executed, and the instruction will be fetched from the new location, and then only it would be executed. So in the program explicitly you do not insert NOP. I think here we finish, and we shall discuss the PIC peripherals in the next class.